Welcome, dear friend, to a gentle ascent into wonder. Tonight, we'll climb together, not with aching muscles or gasping breath, but with curiosity and imagination. We're going to explore mountains, those ancient giants that have watched over Earth for millions of years, silent witnesses to the entire story of life on our planet. Before we begin our journey upward, if these quiet facts bring you peace, a gentle like or subscribe helps others find this calm refuge from the noise of the world. Now, settle deeper into comfort. Let your breathing slow like a climber, finding rhythm, and let's begin our exploration of the sleeping giants that shape our world. Mount Everest grows taller every year. Not by much, just about 4 millimeters annually, roughly the thickness of 4 stacked credit cards, but it rises nonetheless. The Himalayan range gains height because the Indian subcontinent continues pushing northward into Asia at roughly the same speed your fingernails grow, approximately 1.6 inches per year. This collision has been ongoing for 50 million years, crumpling the Earth's crust like fabric gathering in folds, creating the highest peaks our planet has ever known. These mountains are young in geological terms, still growing, still rising, monuments to forces that dwarf human power, yet operate with the patience of stone. But here's what troubles scientists. Everest might not be the tallest mountain on Earth, measured from base to summit. Mauna Kea in Hawaii towers 33,500 feet, nearly 4,500 feet taller than Everest's 29,032 feet above sea level. The difference lies in perspective. Everest rises from high Tibetan Plateau, already elevated miles above the ocean. Mauna Kea rises from the Pacific seafloor, more than 19,700 feet of its height, hidden beneath waves. If you could drain the ocean and stand at Mauna Kea's true base, you'd face a climb that would make Everest seem almost modest by comparison. The Earth keeps its most impressive architecture partially submerged, visible only to those who know where to look. Mountains cover roughly 1/4 of Earth's land surface, yet hold secrets for more than half of humanity. Over 50% of the world's population depends on mountains for fresh water. Every major river system on Earth originates in mountains: the Nile, the Amazon, the Yangtze, the Mississippi. Mountains capture moisture from passing clouds, store it as snow and ice, then release it gradually through springs and streams that feed valleys far below. They are Earth's water towers, vital infrastructure built by tectonic forces over millions of years, operating without maintenance or oversight, providing a service that would be impossible to replicate artificially at any cost. The oldest mountains on Earth have nearly vanished. The Barberton Greenstone Belt in South Africa contains rocks 3.5 billion years old, remnants of mountains that once rivaled the Himalayas in height, but wind, rain, ice, and time have worn them down to gentle hills barely noticeable in the landscape. Mountains are temporary features. In geological terms, they rise through tectonic violence, then spend hundreds of millions of years eroding away, returning to the sea as sediment that will eventually be uplifted into new mountains elsewhere. The rock you stand on today might have been Mountain Peak a billion years ago, might be Mountain Summit again in the distant future. Mountains are Earth's way of recycling its surface, a process that never stops and never repeats exactly the same way. Olympus Mons, on Mars, is the largest volcano and mountain in the entire solar system. This shield volcano rises 72,000 feet, nearly 2.5 times taller than Everest. Its base spans 370 miles across roughly the distance from Los Angeles to San Francisco. If you stood at its center, the edges would be beyond the horizon in every direction, and the slope is so gradual, only 5 degrees on average. You might not realize you were climbing a mountain at all until you looked back and saw the landscape falling away beneath you. The summit would be in space by Earth standards, above 99% of our atmosphere. Mars, with its weaker gravity and lack of plate tectonics, can build mountains that would collapse under their own weight on Earth. Our planet's strength limits its peaks, a reminder that every world has different constraints, different possibilities. The highest peak on every continent tells a story of how that landmass formed. Everest speaks of continental collision. Denali in North America rises from tectonic compression where the Pacific Plate subducts beneath Alaska. Aconcagua in South America owes its height to the Nazca Plate diving under the continent, buckling the crust upward. Kilimanjaro in Africa is a volcanic peak born from the East African Rift, where the continent slowly tears itself apart. Each mountain is a monument to specific geological processes, a frozen moment in Earth's endless tectonic conversation with itself. K2, the second highest mountain on Earth, kills 1 person for every 4 who reach its summit, a fatality rate 5 times higher than Everest. The mountain's steep faces, unpredictable weather, and remote location make it exceptionally dangerous. It has never been climbed in winter until 2021, when a team finally summited in January after decades of failed attempts. K2 is sometimes called the Savage Mountain, a peak that seems to resist human presence more fiercely than any other. Mountains are not merely obstacles to be conquered. They are dynamic environments that set their own terms, indifferent to human ambition or desire. Mountains create their own weather. As moist air rises up a mountain slope, it cools, causing water vapor to condense into clouds and precipitation. This is why one side of a mountain range can be lush rainforest while the other side is desert. The Cascade Range in the Pacific Northwest demonstrates this perfectly. Western slopes receive over 100 inches of rain annually, nurturing temperate rainforests, while eastern slopes get less than 10 inches, creating sagebrush desert. The mountains stand like walls, squeezing moisture from passing air, creating stark divisions in climate over distances of just a few dozen miles. The rain-shadow effect has shaped human history. The Himalayas block moisture from reaching Central Asia, creating the Gobi Desert and influencing the development of civilizations across the region. The Andes create desert on South America's western coast. The Atacama Desert is one of the driest places on Earth, with some areas receiving no measurable rainfall for decades. Mountains don't just change local weather. They influence continental and even global climate patterns, steering wind currents and precipitation across thousands of miles. Mount Chimborazo in Ecuador, though only 20,564 feet above sea level, has a summit farther from Earth's center than any other point on land. Earth bulges at the equator due to its rotation, and Chimborazo sits nearly on the equator. The peak is about 6,800 feet farther from Earth's center than Everest's summit, making it technically the highest point on Earth when measured from the planet's core. Geography is a matter of perspective. Different measuring systems produce different answers, and both can be equally valid. The question, what's the highest mountain, has multiple correct answers depending on how you define highest. Mountains are younger than the dinosaurs, but older than mammals. The Appalachian Mountains in eastern North America formed roughly 480 million years ago, long before the first dinosaurs appeared 230 million years ago. But they've been eroding ever since, wearing down from Himalayan heights to gentle peaks rarely exceeding 6,000 feet. Meanwhile, the Rockies in western North America are relative youngsters, mostly uplifted 50 to 80 million years ago, after the dinosaurs, but during the age of early mammals. The Alps in Europe are younger still, rising within the past 30 million years. Mountains have different ages, different life stages, like forests, where ancient oaks stand beside young saplings. No mountain on Earth is tall enough to reach space. The boundary where atmosphere becomes space-Dakar, mine lines 62 miles above sea level. Everest reaches barely 5.5 miles up, less than 1/10 the height needed to escape Earth's atmosphere. Even if you could stack all the highest mountains on Earth on top of each other, you still wouldn't reach space. Our planet's peaks, as impressive as they seem to us, are just wrinkles on the surface, irregularities on a sphere that's nearly 8,000 miles in diameter. From the perspective of space, Earth appears perfectly smooth, its mountains too small to cast shadows visible from orbit. The Andes form the longest continental mountain range on Earth, stretching 4,300 miles from Venezuela to Chile, roughly the distance from New York to Berlin. This chain of peaks runs along the entire western edge of South America, a monument to the ongoing collision between the Nazca Oceanic Plate and the South American Continental Plate. The range contains hundreds of peaks over 20,000 feet and dozens of active volcanoes that occasionally remind the continent that the mountains are still being built, still growing, still active participants in Earth's geological drama. Mountains influence the evolution of life in remarkable ways, isolated by elevation and climate. Mountain environments create sky islands where species evolve independently from their lowland relatives. The Galapagos finches are famous for island isolation. But mountain peaks create similar effects. A mouse species living on one mountain peak may be genetically distinct from the same species on a neighboring peak just a few miles away because the valley between them is an uncrossable barrier. Mountains breed diversity through isolation, creating laboratories of evolution scattered across the landscape. The tree line, the elevation above which trees cannot grow, varies dramatically depending on latitude. In the tropics, trees can grow up to 15,000 feet or higher. In Alaska, the tree line might be only 2,000 feet. The pattern follows temperature. Colder climates push the tree line lower. Warmer climates allow it higher. But individual mountains complicate the pattern through local weather, soil conditions, and exposure. Walking up a mountain takes you through climate zones equivalent to traveling thousands of miles toward the poles, from temperate forest through subalpine meadows to alpine tundra to permanent ice and snow, all compressed into a vertical journey of a few thousand feet. Alpine tundra exists only on mountaintops and in polar regions, a specialized ecosystem that covers just 3% of Earth's land surface. Plants here grow low to the ground, often in cushion or mat forms, to resist fierce winds. Growing seasons last only weeks, and some alpine plants live for centuries, adding growth so slowly that annual rings can only be seen under microscopes. Flowers bloom in bursts of color against gray rock, defiant splashes of life in an environment that seems to forbid it. These plants have mastered the art of patience, waiting months for a brief opportunity to photosynthesize, flower, and set seed before winter returns. Glaciers carved the most dramatic mountain landscapes during the ice ages. U-shaped valleys, hanging valleys, cirques, arêtes, Hornzoll. These features result from ice slowly grinding away rock over thousands of years. Glaciers move like rivers of ice, flowing downhill under their own weight, but unlike rivers, they carry rocks embedded in their bases, using them like sandpaper to sculpt the landscape. Yosemite Valley in California is a classic example. Walls rising 3,000 feet straight up from a flat valley floor. Waterfalls plunging from hanging valleys. All created by glacial carving during the Pleistocene ice ages that ended only 12,000 years ago. Mount Fuji last erupted in 1707. Covering Tokyo in volcanic ash despite being 60 miles away. The volcano has erupted at least 16 times in recorded history, and geologists consider it certain to erupt again. The question is when, not if. Yet more than 300,000 people climb Fuji each summer, following ancient pilgrimage routes to the summit. The mountain is sacred in Japanese culture, symbol of the nation itself. An almost perfect volcanic cone rising 12,388 feet above the surrounding plain. Humans have always been drawn to mountains despite their dangers, perhaps because of them, seeking meaning in places where earth reaches toward sky. The deepest canyon on earth isn't the Grand Canyon. The Yarlung Tsangpo Canyon in Tibet reaches depths of 17,567 feet, over 3 miles from rim to river, making it nearly twice as deep as the Grand Canyon. The river cuts through the eastern Himalaya between two peaks over 25,000 feet high, creating a gorge so deep and remote that large sections remained unexplored until the 1990s. Some believe the canyon might contain waterfalls taller than any yet discovered, hidden in gorges so inaccessible that they've never been seen by human eyes. Mountains keep secrets even in our age of satellites and GPS. Denali in Alaska appears taller than Everest when seen from the ground because it rises abruptly from near sea level. Everest sits on the Tibetan Plateau, already elevated over 15,000 feet, so the mountain gains only about 14,000 feet of prominence above its surroundings. Denali rises 18,000 feet above its base in just a few horizontal miles. A wall of stone and ice that dominates the landscape, unlike any other peak in the world. Vertical relief, how much a mountain rises above its surroundings, often impresses the eye more than absolute elevation. And by this measure, Denali is arguably the most spectacular mountain on the planet. Mountain ranges follow patterns across Earth's surface that reveal our planet's tectonic past. The Appalachians in North America align with mountains in Scotland and Scandinavia, because they were once part of the same range before the Atlantic Ocean opened 200 million years ago, splitting the mountains in two. Rocks in the eastern United States match rocks in Morocco. Fossils in Australia match fossils in Antarctica. Mountains remember when continents were joined, holding evidence of ancient geographies in their stones, like memory written in granite and schist. The Matterhorn in the Alps has one of the most recognizable profiles of any mountain, nearly perfect pyramid rising 14,692 feet above sea level. Its distinctive shape results from glacial erosion on all sides simultaneously, carving the mountain into a horn peak where multiple glacial cirques meet. The Matterhorn killed more than 500 climbers before modern equipment and techniques made it relatively safer, though it remains dangerous and demanding. Some mountains seem designed to attract human ambition and test human limits, their shapes calling to something deep in our nature that responds to vertical challenges. Mountains trap clouds and create persistent weather systems that can last for days or weeks. Lenticular cloud smooth, lens-shaped clouds form when moist air flows over mountains, creating standing waves in the atmosphere. These stationary clouds can hover over peaks for hours, growing at their upwind edge as moisture condenses and evaporating at their downwind edge as air descends and warms. From a distance, they look like alien spacecraft, perfectly smooth and unnaturally still, while other clouds rush past. Mountains are sculptors of air as well as rock, shaping wind and water into forms that seem almost alive. The highest permanently inhabited settlement on Earth sits at 16,732 feet in the Peruvian Andes. La Rinconada, a gold mining town, clings to a glacier where more than 50,000 people live and work in conditions that would seem impossible to lowland dwellers. At this elevation, the air contains only half the oxygen available at sea level. Newcomers gasp with every step, their hearts racing, bodies struggling to extract enough oxygen from the thin atmosphere. Yet children are born here. Families have lived here for generations. Their bodies adapted through physiology and cultural knowledge to thrive where most humans would quickly perish. Mountains don't just challenge us, they reveal our remarkable capacity for adaptation. Your body changes when you ascend into thin air. Within hours of reaching high altitude, your breathing rate increases and your heart beats faster, trying to deliver more oxygen to tissues starving for it. Over days and weeks, your body produces more red blood cells to carry oxygen more efficiently. Your capillaries multiply, reaching deeper into tissues. Your mitochondria, the power plants of your cells, become more efficient at using whatever oxygen they receive. Some of these changes reverse when you return to sea level. But people who spend years at high altitude may permanently remodel their physiology, becoming more efficient oxygen users even at lower elevations. The Sherpas of Nepal possess genetic adaptations to high altitude that lowland people lack. Specific genes help their bodies use oxygen more efficiently and produce hemoglobin, the oxygen-carrying molecule in blood, in different proportions than sea level populations. These adaptations arose over thousands of years of living at elevations where most humans struggle to survive. Similarly, Tibetan highlanders and Andean populations show distinct genetic adaptations to altitude, evolved independently on different continents. Mountains have shaped human genetics, creating biological diversity as real as the diversity of languages and cultures. Mount Kilimanjaro rises from African savanna to Arctic conditions in just 15,000 vertical feet. You can begin your climb in 80-degree heat among elephants and giraffes, then finish days later in below-zero temperatures among glaciers and ice fields. The mountain compresses multiple climate zones into a single vertical journey: rainforest, giving way to heath and moorland, then alpine desert, then ice. Yet Kilimanjaro's glaciers are disappearing, shrunk by more than 80% since 1912. Scientists debate the exact causes: climate change, land use patterns, natural climate cycles, but the ice retreats, regardless of our understanding, marking time in a way glaciers have always done, expanding and contracting with climate shifts that operate on scales both shorter and longer than human lifetimes. Glaciers are rivers of ice that flow downhill under their own immense weight, but they move so slowly that they appear frozen in time to human perception. Most glaciers flow only inches or feet per day. Though some move faster, the Jakobshovs Glacier in Greenland flows up to 150 feet per day, among the fastest on Earth. The ice deforms plastically under pressure, flowing like cold honey, carrying rocks and boulders in its grip. Glaciers have carved some of Earth's most spectacular landscapes: Yosemite, the Matterhorn, the fjords of Norway's sculpting stone, with patience measured in millennia. The death zone, above 26,000 feet on high mountains, describes elevations where the human body cannot acclimatize. At these heights, your body consumes itself, breaking down muscle tissue faster than it can rebuild, losing weight and strength with each passing hour, regardless of how much you eat. Climbers in the death zone are dying slowly, racing against their own physiology to reach the summit and descend before their bodies fail completely. Sleep becomes difficult or impossible. Judgment deteriorates. Frostbite claims fingers and toes. Every decision matters because the margin for error shrinks to nothing. Mountains at extreme altitude don't just test physical endurance, they push consciousness itself to its limits. Over 200 bodies remain on Mount Everest, frozen in the positions where they died, many serving as landmarks for climbers following the same routes. Green Boots, a climber who died in 1996, lay in a small cave along the Northeast Ridge route for years, passed by hundreds of subsequent climbers. The mountain is too dangerous and the bodies too difficult to retrieve at such extreme altitudes. Most died during descent. After successfully reaching the summit, their energy and judgment depleted by the effort of climbing. Mountains demand respect, not just on the way up, but especially on the way down. When exhaustion and overconfidence combine into deadly complacency, avalanches kill more mountaineers than any other hazard. These rivers of snow can flow at 80 miles per hour, carrying thousands of tons of snow and ice that can bury a person under 10 feet of debris in seconds. The snow sets like concrete almost immediately, and victims have only minutes before suffocation occurs. Avalanche survival depends on being found quickly, usually by companions carrying beacons that can locate buried transmitters. Mountains covered in snow exist in constant tension between stability and catastrophe, and the triggers can be subtle: a slight temperature change, additional snowfall, vibrations from wind, or human activity. The slope remembers every stress, and avalanches release when the accumulated burden exceeds the snow's strength to hold itself in place. The Himalayas contain 14 peaks, over 26,000 feet tall, 14 of the world's highest mountains concentrated in a single range spanning 1,500 miles across 6 countries. No other mountain range comes close to these heights. The Andes, despite being longer, have no peak higher than 23,000 feet. The Rockies top out around 14,500 feet. The Alps barely exceed 15,700 feet. The Himalayas stand alone in their elevation, a region where Earth's crust has been squeezed upward to heights unmatched anywhere else on the planet. These mountains are Earth showing off, demonstrating the upper limits of what tectonic forces can build, given the right collision, the right rocks, the right timing. Mountains affect global weather patterns in ways that influence continents thousands of miles away. The Tibetan Plateau, elevated more than 15,000 feet and covering an area larger than Alaska, absorbs enormous amounts of solar radiation during summer, heating the air above it and creating low-pressure systems that draw in moist air from the Indian Ocean. This process drives the Asian monsoon, which delivers rain to billions of people across South and Southeast Asia. Without the Tibetan Plateau, the monsoon would be weaker or might not exist at all, transforming the climate of half of Asia. Mountains don't just change local weather, they're essential components of Earth's atmospheric circulation, steering winds and rain across entire hemispheres. The Rocky Mountains extend over 3,000 miles from New Mexico to northern Canada. But they're not a single mountain range. They're dozens of ranges with different origins, ages, and characteristics grouped under one name for convenience. The Southern Rockies rose from ancient continental collisions. The Middle Rockies formed from magmatic intrusions and volcanic activity. The Northern Rockies have yet different origins, involving complex thrust faulting. Naming conventions simplify geography for human understanding, but mountains don't care what we call them. Each peak has its own story, its own unique path, from seafloor sediment to erosional remnant. Mount Rainier looms over Seattle and Tacoma, an active volcano that last erupted in the 1840s and will certainly erupt again. The mountain holds more glacial ice than all other Cascade Range. Volcanoes combined about 35 square miles of ice and snow that would melt catastrophically during an eruption, creating Lahar's volcanic mudflows that can travel 50 miles per hour down valleys. These flows would follow rivers that now hold suburban communities, potentially endangering hundreds of thousands of people. Yet, life continues normally in the mountain's shadow, a calculated acceptance of risk in exchange for the beauty of living within sight of one of North America's most magnificent peaks. Mountains can generate earthquakes through their sheer weight. The Himalayas are so massive that they depress Earth's crust beneath them, creating stress that occasionally releases as earthquakes. The 2015 Nepal earthquake killed nearly 9,000 people and was triggered by stress related to the ongoing collision between the Indian and Eurasian plates. The same collision that builds the mountains continues to shake them. Mountains are not stable monuments, but dynamic features of an active planet, rising through violence and occasionally reminding us that the forces that created them continue operating beneath the surface. The Alps rise roughly 2 millimeters per year, despite constant erosion removing material from their peaks. The collision between the African and Eurasian plates continues pushing the mountains upward, a race between tectonic uplift and erosion that currently favors the mountains. But erosion is patient and relentless. Over tens of millions of years, erosion will win, wearing the Alps down to stumps as it has worn down older mountain ranges before them. The question is not whether mountains will erode away, but how long they can maintain their height against the persistent attack of water, ice, and wind. Fjords are flooded glacial valleys where the sea has invaded land. Norway's fjords cut 120 miles inland in places, steep-walled valleys, carved by ice during the Pleistocene, and then filled with ocean water when the glaciers retreated and sea level rose. The walls can rise 4,000 feet straight up from water. That's 4,000 feet deep, nearly 1.5 miles of vertical relief in places. These drowned mountains create some of Earth's most dramatic coastlines, places where mountains meet ocean in configurations found nowhere else. Unique to latitudes and geologies that allowed massive glaciers to carve valleys below sea level, mountains store water as snow and ice, releasing it gradually through melting in spring and summer. This natural reservoir system provides steady water flow even during dry seasons, making agriculture possible in regions that would otherwise struggle with water scarcity. The Ganges, Indus, Brahmaputra, Yangtze, and Yellow rivers all depend on Himalayan snowmelt to maintain their flows, supporting over 2 billion people downstream. Mountains are not just scenic features, but essential infrastructure in the global water cycle, capturing and storing precipitation in frozen form, then releasing it on schedules determined by temperature and season rather than rainfall patterns. But glaciers worldwide are retreating as global temperatures rise. Most mountain glaciers have been shrinking since the mid-20th century, with acceleration in recent decades. Smaller glaciers may disappear within our lifetimes, and larger glaciers are thinning and retreating up their valleys. This affects water supplies for communities that depend on glacial melt, creating a paradox. Warming initially increases meltwater flow, providing abundant water. But as glaciers shrink, the total volume of stored ice decreases, eventually reducing the reliable water supply that glaciers have provided for millennia. Mountains are changing in real time, responding to atmospheric changes faster than the rocks themselves rise or erode. Puncak Jaya in Indonesia, at 16,024 feet, is the highest island peak in the world and the highest point between the Himalayas and the Andes. This mountain sits just 4 degrees from the equator, yet holds glaciers' ice fields that have persisted for thousands of years despite tropical heat. The glaciers are shrinking rapidly and may vanish within decades, ending a frozen presence that has existed on this mountain since before human civilization. Equatorial glaciers are among Earth's most sensitive climate indicators, existing at the edge of what's thermodynamically possible, maintained only by the cooling effect of high elevation, barely overcoming tropical warmth. Mountains create biodiversity hotspots by providing varied habitats across short distances. A single mountain might host desert species at its base, temperate forest species on lower slopes, subalpine meadow species higher up, and Arctic-adapted species near the summit. Animals and plants can shift their ranges vertically as climate changes, moving up or down the mountain to track their preferred temperature zones. But this refuge has limit. Species adapted to high elevations have nowhere to go as temperatures rise. They're pushed upward until they run out of mountain, their habitat shrinking to a smaller and smaller area as the climate warms, until finally there's no more up left. The Drakensberg Mountains in South Africa contain caves with rock art created by sand people over thousands of years. These paintings depict eland, humans, mysterious therianthropes, part human, part animal figures, and scenes that might represent shamanic journeys or spiritual experiences. Mountains have always held sacred significance for human cultures, places where earth meets sky, where spirits dwell, where the ordinary world gives way to something transcendent. Our ancestors climbed mountains not to conquer them but to connect with forces larger than human life, seeking vision and meaning in high places where the air is thin and perspective expands beyond daily concerns. Mount Kailash in Tibet is sacred to 4 religions: Buddhism, Hinduism, Jainism, and Bonyet, it has never been climbed. The mountain stands 22,028 feet high, technically climbable, but Chinese authorities forbid climbing it out of respect for its religious significance. Pilgrims walk a 32-mile circuit around the mountain, a journey that takes several days and crosses a 18,200-foot pass for believers. Completing this circuit brings spiritual merit and purification. Mount Kailash demonstrates that not all mountains need to be climbed, that some peaks serve humanity better as objects of reverence than conquest. Their summits left pristine and untouched in a world where humans have been almost everywhere. The highest lake in the world is Lake Hoyos del Salado, a crater lake at 20,965 feet on the border between Chile and Argentina. At this elevation, water barely remains liquid. The boiling point drops to about 180 degrees Fahrenheit, and ice can sublimate directly to vapor without melting. The lake is small, only about 100 yards across, and its persistence at such altitude seems almost miraculous. It exists in an environment hostile to life as we normally understand it, yet it endures. A puddle of water near the threshold of space, defying the expectation that such heights should be completely frozen and dry. Volcanoes create mountains in moments. Geologically speaking, Mount St. Helens grew from dormant volcano to active eruption in weeks in 1980, then built a lava dome over 1,000 feet high inside its crater over the following years. Volcanic mountains can appear in decades or centuries rather than the millions of years required for tectonic mountains. Paricutin volcano in Mexico emerged from a farmer's cornfield in 1943 and grew to 1,400 feet high within a year, burying 2 villages under lava and ash. These rapid mountains follow different rules than their tectonic cousins, built from below by magma rather than squeezed upward by colliding plates. The Ring of Fire surrounding the Pacific Ocean contains 75% of Earth's active and dormant volcanoes, more than 450 volcanoes stretching from New Zealand through Indonesia, Japan, Alaska, and down the western coasts of the Americas to Chile. This ring marks the boundaries of tectonic plates, places where oceanic crust descends into Earth's mantle and melts, producing magma that rises to create volcanic mountains. The pattern is so clear from space that it reveals Earth's tectonic machinery in a single image-a horseshoe of fire, announcing where plates meet and mountains are born. Mountains experience extreme weather that would seem impossible at lower elevations. Mount Washington in New Hampshire recorded wind speeds of 231 miles per hour in 1934, the highest wind speed measured at Earth's surface until 1996. The mountain sits where several storm tracks converge, and its 6,288-foot height forces wind upward, accelerating it over the summit. Temperatures there have dropped to -47 degrees Fahrenheit. The combination of wind and cold can produce wind chills below -100 degrees. Mountains create their own extreme weather by disrupting atmospheric flows, accelerating winds, cooling air masses, and generating conditions that exist nowhere else at their latitude. Mountain snow reflects sunlight back into space, helping regulate Earth's temperature. Fresh snow can reflect up to 90% of incoming solar radiation, while bare rock or soil reflects only 10 to 30%. Mountains covered in snow help keep the planet cooler by bouncing solar energy back to space before it can heat the surface. This creates a feedback loop. Warming temperatures melt mountain snow, exposing darker rock, which absorbs more heat, which melts more snow, which exposes more rock. The feedback can accelerate changes, turning gradual warming into rapid transformation as mountains lose their reflective white covering. The continental divide in North America runs along the Rocky Mountains, separating rivers that flow to the Pacific Ocean from those flowing to the Atlantic and Gulf of Mexico. Stand on the divide, and water falling on one side of you eventually reaches different oceans than water falling on the other side. This invisible line, determined entirely by topography, has profound consequences for hydrology, ecology, and human settlement patterns. Mountains don't just rise above the landscape, they organize it, determining where water flows and therefore where forests grow, where animals migrate, where humans settle. Chinook winds, also called Effin winds, warm dramatically as they descend mountain slopes. Moist air rises up the windward side of mountains, cooling and dropping precipitation. The now dry air descends the leeward side, warming at about 5.5 degrees Fahrenheit per 1,000 feet faster than it cooled during ascent, because it's no longer releasing latent heat through condensation. These winds can raise temperatures by 40 degrees in hours, melting feet of snow in a single day. They create strange inversions where mountain valleys are warmer than lower elevations, and they can produce wind speeds that damage buildings and topple vehicles. Mountains transform air masses in complex ways, creating microclimates and weather events that exist only in their presence. The Ural Mountains separate Europe from Asia by convention rather than any dramatic geological boundary. The range is ancient and worn down, rarely exceeding 6,000 feet, but it has served as a cultural and geographic dividing line for centuries. The Urals demonstrate that mountains' importance to human geography often exceeds their physical impressiveness. Low mountains can be significant barriers to travel and communication, while high mountains with good passes might be easily crossed. Geography is both objective fact and human interpretation, and mountains exist in both realms simultaneously. Limestone mountains dissolve slowly in rain. Water slightly acidified by atmospheric carbon dioxide reacts with calcium carbonate in limestone, dissolving it and carrying it away in solution. Over millions of years, this creates karst landscapes, mountains riddled with caves, sinkholes, underground rivers, and towers of stone separated by eroded valleys. The stone forest in China, the karst towers of Guyana, the cave systems of Kentucky and Vietnam result from water patiently dissolving mountains from within and without. These mountains are temporary in a way granite mountains are not, vulnerable to chemical attack that bypasses their physical strength. Caves in mountains can extend for hundreds of miles. Mammoth Cave in Kentucky has over 400 miles of mapped passages, making it the longest cave system in the world. These passages formed as water-dissolved limestone along cracks and joints, gradually enlarging pathways through the rock. Cave formations, stalagmites, flowstone, halictites grow so slowly that some are thousands of years old. Built drop by drop as mineral-laden water deposits calcium carbonate. Mountains are solid but not immutable, hollow but not empty, dark but not lifeless. Entire ecosystems exist in mountain caves, adapted to permanent darkness, fed by water, and organic material flowing in from the surface. Mountains harbor species found nowhere else on Earth. The mountain gorilla lives only in the volcanic mountains of Central Africa. A population of fewer than 1,000 individuals restricted to slopes between 8,000 and 13,000 feet. The snow leopard prowls the high peaks of Central Asia, so elusive that it's called the ghost of the mountains, rarely seen even by people who spend their lives in its habitat. The Himalayan tahr, the Hawaiian silkviscard, the mountain viscachichiche of these species evolved in isolation on specific mountain ranges, becoming so specialized to their high-altitude environments that they cannot survive elsewhere. Mountains are arcs of biodiversity, preserving species that might otherwise have gone extinct as climates changed in the lowlands. Alpine plants have evolved remarkable strategies to survive where few other plants can grow. Some produce dark pigments that absorb maximum sunlight in the brief growing season. Others grow in dense cushions that trap heat and protect against wind. Many are perennials that invest energy in extensive root systems rather than showy growth, living for decades while appearing to barely change. The Welwitschia plant in Namibia's desert mountains can live over 1,000 years, surviving on fog moisture alone. These plants teach patience. They measure success not in rapid growth, but in persistent survival, outlasting harsh years to reproduce when conditions allow. Edelweiss, the iconic alpine flower, grows dense woolly hairs that protect it from intense ultraviolet radiation at high altitude. The atmosphere is thinner on mountains, filtering less UV light, and plants must defend themselves against radiation that would damage their tissues. The white, fuzzy appearance that makes Edelweiss recognizable is actually survival armor, proof that beauty often emerges from adaptation to harsh conditions. Mountains select for resilience, and what we perceive as aesthetic appeal is frequently the visible expression of sophisticated survival strategies honed over millions of years. The ptarmigan, a grouse that lives in alpine and Arctic environments, changes color with the seasons: white in winter to match snow, mottled brown in summer to match rocks and vegetation. This bird even grows feathered feet in winter, natural snowshoes that let it walk on powder without sinking. Migration for ptarmigans doesn't mean flying thousands of miles south. It means moving a few hundred feet downslope when winter storms make the highest elevations uninhabitable. For mountain creatures, vertical migration of a few hundred feet can be equivalent to horizontal migration of hundreds of miles, crossing climate zones without traveling far from home. Mountains create temperature inversions where valleys are colder than slopes. Cold air is denser than warm air, so it flows downhill like invisible water, pooling in valleys, while warmer air remains on mid-elevation slopes. On calm, clear nights, the temperature difference can exceed 20 degrees Fahrenheit, with valley floors freezing, while slopes 1,000 feet higher remain above freezing. This affects where farmers can grow frost-sensitive crops, where orchards are planted, where ancient villages were built. People living in mountains have always known that location matters. A few hundred feet of elevation can mean the difference between frost and warmth, between crop failure and harvest. The monarch butterfly migration includes an often overlooked vertical component. Monarchs that overwinter in Mexico's mountain forests cluster in Oyamel fir trees at elevations between 9,000 and 11,000 feet. The cool mountain temperatures slow their metabolism, allowing them to survive winter on stored fat reserves without feeding. Too cold, and they freeze. Too warm, and they burn through energy too quickly and starve. The mountains provide a narrow altitude band where temperatures fall within the precise range needed for survival, Goldilocks zone that exists only on these particular slopes at these particular elevations. Glacial lakes glow brilliant turquoise because of rock flour-fine sediment ground to powder by glaciers and suspended in the water. This sediment is so fine that it scatters light, absorbing red wavelengths and reflecting blue-green, creating colors so vivid they appear artificial. Lake Louise in Canada, Peto Lake, the pools below Patagonian glaciers all share this otherworldly color. The beauty is a side effect of destruction. Evidence of rock being pulverized grain by grain as glaciers grind downward, turning solid stone into powder suspended in meltwater. Even destruction can be beautiful when viewed at the right scale. Mountain glaciers create their own winds. Cold, dense air flows off ice fields and down valleys in persistent breezes called katabatic winds. These winds can blow steadily for hours or days, carrying the chill of ice to valleys far below. In Antarctica, katabatic winds can exceed 100 miles per hour as air accelerated by both temperature difference and gravity races down ice sheets thousands of feet thick. Mountains and ice together create weather systems that persist day and night, independent of the sun's heating and cooling cycles that drive most winds. The tree line marks a boundary determined by temperature, but also by wind, soil depth, water availability, and historical accidents of seed dispersal. Islands of trees sometimes grow above the general tree line, where local conditions, a sheltered valley, a water source, deeper soil create microclimates favorable for tree survival. These isolated groves are pioneers testing the limits of where trees can grow, and they might expand upward if climate warms or contract downward if conditions deteriorate. The tree line is not a fixed wall, but a dynamic boundary that shifts over decades and centuries, responding to climate changes both subtle and dramatic. Krummholz, German for crooked wood, describes the twisted, stunted trees that grow at treeline, shaped by constant wind and ice. These trees might be centuries old, yet only a few feet tall, growing horizontally along the ground where wind is slightly slower. Their windward branches die back, while leeward branches survive, creating flag-like shapes pointing away from prevailing winds. These trees are survivors, growing where conditions almost, but not quite, prevent tree life. Existing in the narrow zone where possible meets impossible, they demonstrate that life's boundaries are fuzzy rather than sharp, that living things persist in transitional zones we might declare uninhabitable. Mountains amplify the sound of silence, absent the noise of traffic, machinery, and crowds. High mountains can be profoundly quiet, especially when snow covers the ground and absorbs what little sound exists. In this silence, you hear things normally masked: your own heartbeat, blood moving through vessels near your ears, the quiet creak of snow settling. This silence isn't absence, but presence, a different quality of sound that feels almost tangible. Mountains offer something increasingly rare in the modern world: the experience of true quiet, the chance to hear subtle sounds normally drowned out by the constant background noise of civilization. The Great Dividing Range in Australia runs 2,300 miles along the eastern coast, influencing weather patterns across the continent. Despite being relatively low, Mount Kosciuszko, the highest peak, reaches only 7,310 feet. The range captures moisture from Pacific weather systems, creating a green coastal strip and leaving inland areas dry. Australia is the flattest continent, and even these modest mountains have outsized importance in determining where rain falls and therefore where forests grow, where rivers run, where cities developed. Geography's influence doesn't always correlate with dramatic elevation. Ellen's small mountains can cast large shadows. Mountains erode through mass wasting, the downslope movement of rock and soil under gravity's influence. Rockfalls, landslides, debris flows, and soil creep all contribute to wearing mountains down. Massive landslides can move billions of tons of rock in minutes, reshaping valleys and damming rivers. The Flims rock slide in Switzerland 10,000 years ago moved 4 cubic miles of rock, creating a debris field still visible today. Mountains don't just erode grain by grain through water and ice, sometimes they collapse spectacularly. Entire mountainsides sliding into valleys below, moving more material in moments than streams could transport in centuries. Permafrost, permanently frozen ground, exists in high mountains, even in temperate latitudes. The soil and rock freeze solid below a thin surface layer that thaws each summer, and this frozen ground can persist for thousands of years. Permafrost provides structural support for slopes, holding them together like natural concrete. As climate warms and permafrost thaws, mountains become less stable. Rock faces that have been solid for millennia suddenly release, triggering rockfalls in areas previously stable. Mountains frozen since the Ice Age are now waking up, adjusting to warmth they haven't experienced in thousands of years. The Himalayas contain more ice than anywhere outside the polar regions, earning them the nickname the Third Pole. Estimates suggest the range holds 600 billion tons of ice in approximately 15,000 glaciers. This ice stores water that eventually flows to some of Earth's largest river systems, supporting ecosystems and human populations across Asia. But the Himalayas are warming faster than the global average, what scientists call elevation-dependent warming, and glacier loss is accelerating. The ice that took thousands of years to accumulate is disappearing in decades. A transformation happening so rapidly that maps become outdated before they're printed. Altitude affects how food cooks. Water boils at 212 degrees Fahrenheit at sea level, but at 10,000 feet, it boils at only 194 degrees. This lower temperature means cooking takes longer. You can't hard-boil an egg properly on Everest, no matter how long you boil it, because the water never gets hot enough. Baking becomes unpredictable as lower air pressure affects how dough rises. Mountaineers carry pressure cookers to high camps, devices that trap steam to raise cooking temperatures. Even eating becomes complicated at high altitude. A reminder that the familiar rules of sea level existence don't apply in the thin air of high mountains. Mountains modify cosmic radiation reaching Earth's surface. Atmosphere shields us from harmful radiation from space, but there's less atmosphere above mountain peaks. Cosmic ray exposure at 10,000 feet is about twice the exposure at sea level. People living at high altitude receive slightly more radiation over their lifetimes than sea level populations. Not enough to cause obvious harm, but measurable. Astronauts on the International Space Station, pilots on frequent high-altitude flights, and people who live on mountains all experience increased cosmic ray exposure. Mountains bring us slightly closer to space and its hazards. The highest mountain in the solar system, known outside Earth and Mars, is Iapetus Ridge on Saturn's moon, Iapetus. This ridge runs 800 miles along the moon's equator and rises 12 miles above the surrounding surface, more than twice Everest's height. Scientists remain uncertain how it formed. Hypotheses include material falling from a destroyed ring system, tectonic processes, or some combination of forces unique to this icy moon. Every solid world with sufficient gravity develops mountains through one mechanism or another. Mountains seem to be a universal feature of planetary geology, evidence that surfaces under stress inevitably buckle and fold. Mountain sickness affects about 75% of people who rapidly ascend above 8,000 feet. Symptoms include headache, nausea, dizziness, and fatigue, your body protesting insufficient oxygen. Most cases are mild and resolve with rest and acclimatization, but severe cases can develop into high-altitude pulmonary edema or cerebral edema fluid, accumulating in lungs or brain, which can be fatal if the person doesn't descend immediately. The only real cure for serious altitude sickness is descent, going down where air is thicker and oxygen more abundant. Mountains set physiological limits that technology cannot overcome, boundaries written in blood chemistry and oxygen partial pressure. Traditional mountain peoples developed cultures adapted to high-altitude life over thousands of years. The Quechua and Aymara of the Andes, the Sherpa and Tibetan peoples of the Himalayas. These cultures possess not just genetic adaptations, but accumulated knowledge about living where most humans cannot survive. They know which plants indicate good pasture, which weather signs mean storms are coming, which routes are safe in which seasons. This knowledge represents thousands of years of observation and experience, wisdom earned through trial and error, success and tragedy. Mountains have shaped these cultures as surely as they've shaped their genetics. Transhumance, seasonal movement of livestock between mountain and lowland pastures, has been practiced for millennia. In summer, herders drive sheep, goats, or cattle to high mountain meadows where grass grows lush in the brief, warm season. In autumn, they return to lowland valleys before snow makes the high pastures inaccessible. This practice shaped landscapes across Europe, Asia, and the Americas, creating trails still visible today, supporting economies and cultures that treated mountains not as barriers but as resources to be used seasonally. Mountains offered summer abundance to people who understood their rhythms and accepted their terms. Mountain passes determined trade routes and cultural exchange for thousands of years. The Khyber Pass between Afghanistan and Pakistan, the Brenner Pass through the Alps, the Cumberland Gap through the Appalachians. These routes channeled movement through otherwise impassable mountain barriers. Cities developed at the entrances to passes, controlling access and taxing trade. Armies fought for control of passes, knowing that whoever held the mountain gates controlled movement between regions. Mountains didn't stop human migration and trade, but constrained them, funneling them through specific routes that acquired historical importance, far exceeding their physical features. The sound of mountains falling is surprisingly quiet at a distance. Massive rock slides involving millions of tons of rock can collapse in near silence when viewed from miles away because sound dissipates over distance. Closer observers report sounds like thunder or freight trains, but from a distance, an entire mountainside can rearrange itself in eerie quiet, like watching catastrophe with the volume turned off. This disconnect between visual drama and auditory absence creates surreal experiences, reminding us that our senses evolved for human-scale events and sometimes fail to convey the magnitude of geological processes. Mountains preserve history in ice. Glaciers accumulate snow year after year, and each layer contains atmospheric gases, dust, pollen, and chemical signatures of its time. Ice cores drilled from glaciers provide climate records spanning thousands of years of frozen archive of atmospheric history. Scientists can identify volcanic eruptions from sulfate layers, industrial pollution from heavy metal concentrations, even nuclear weapons testing from radioactive isotopes. Mountains have been recording climate history in ice for millennia, creating libraries we're only now learning to read, finding in frozen water a detailed account of how Earth's atmosphere has changed through human history and before. Some mountains are optical illusions. Fata Morgana mirages can make distant mountains appear to float above the horizon or seem taller than they are. Temperature inversions bend light, creating false images that shift and waver. Sailors have reported seeing mountains where none exist, islands where maps show only ocean. Our eyes evolved to interpret light traveling through atmosphere of consistent density, but mountains create atmospheric variations that bend light in unexpected ways, producing illusions that seem impossible until you understand the optics involved. The shadow of a mountain can extend for hundreds of miles. Mount Rainier casts a triangular shadow eastward at sunrise that can reach beyond the horizon, a dark pyramid projected across the atmosphere by the rising sun. From the summit of tall mountains at sunrise or sunset, you can sometimes see the mountain's shadow extending through the atmosphere to the horizon, a perfectly triangular projection that seems to reach into infinity. These shadows exist only in specific conditions of light and atmosphere, ephemeral phenomena that remind us mountains influence not just land but air and light. Mountains collect atmospheric pollution even in remote locations. Pesticides, heavy metals, and other pollutants travel through the atmosphere and concentrate in mountain snowfall, which then releases them as glaciers melt. Polar bears in the Arctic show pollutants manufactured thousands of miles away. Fish in high mountain lakes contain mercury despite being nowhere near industrial sources. Mountains demonstrate that there are no truly pristine places left on Earth. Atmospheric circulation connects all locations, and pollution released anywhere eventually reaches everywhere, including the most remote peaks humans rarely visit. The highest astronomical observatory sits at 18,405 feet on Lulalaco volcano in Chile. At this elevation, the atmosphere is so thin and dry that telescopes can observe wavelengths of light absorbed by water vapor at lower elevations. The air is steady and clear, with minimal light pollution, making it ideal for astronomy. Observatories cluster on mountains worldwide: Hawaii's Mauna Kea, Chile's Atacama Desert, the Canary Islands, places where thin air, clear skies, and distance from cities create optimal viewing conditions. Mountains bring us closer to space in practical ways, reducing the atmosphere we must look through to study the universe. Gravity is measurably weaker on mountain peaks. Newton's law of gravitation states that gravitational force decreases with distance from Earth's center, and mountain peaks are farther from the center than sea level, a few miles farther for the highest peaks. The difference is tiny, about 0.3% weaker gravity on Everest than at sea level. but it's real and measurable with sensitive instruments. You weigh slightly less on a mountain summit than at the beach, though the difference is so small you'd never notice. Mountains remind us that even constants like gravity vary subtly with location. The oldest living things on Earth grow on mountains. Bristlecone pines in California's White Mountains include individuals over 5,000 years old. They were saplings when the pyramids were being built, growing slowly in harsh conditions where competitors cannot survive. The oldest verified bristlecone, named Methuselah, has been growing for 4,853 years, and there may be even older individuals not yet documented. These trees grow in locations so harsh that a year's growth can be thinner than a hair, rings so tight they're difficult to distinguish. Harsh conditions, paradoxically, extend life. Fast growth means fast death, but slow growth in difficult environments can mean millennia of persistence. Mountains move in earthquakes by meters in seconds. The 2015 Nepal earthquake shifted Mount Everest southward by about 1.2 inches and decreased its height by roughly 1 inch. The 2011 Japan earthquake moved the island of Honshu 8 feet eastward and shifted Earth's axis by about 4 inches. Mountains that seem eternal and unchanging can lurch sideways in the span of a heartbeat. Reminders that the solid ground beneath our feet is neither solid nor stationary on geological timescales. We perceive stability because we live briefly, but mountains experience constant transformation, rising and falling, shifting and settling through processes that never stop. The snow line, the lowest elevation, where snow persists year-round, varies dramatically by latitude and local climate. In the tropics, permanent snow exists only above 15,000 feet or higher. In Alaska, the snow line can be as low as 3,000 feet. In Antarctica, it reaches sea level. This variation reflects temperature patterns. Colder climates allow snow to persist at lower elevations. Warmer climates push the snow line higher. But local factors complicate the patterns. South-facing slopes receive more sun and have higher snow lines than north-facing slopes. Wet climates allow lower snow lines than dry climates because more snow falls. Mountains create microclimates where these factors combine in infinite variation. Some mountains grow glaciers even in deserts. The Karakoram Range in Pakistan experiences a phenomenon called Karakoram anomaly. While most Himalayan glaciers shrink, some Karakoram glaciers are stable or even advancing. Scientists believe this results from changing precipitation patterns, bringing more snowfall to these high peaks despite warming temperatures. The increased snow may insulate glacier ice, preventing melt. Mountains don't respond uniformly to climate change. Local conditions create exceptions to regional trends. Pockets of growth amid general retreat, complexity that defies simple narratives. Mountain lakes can explode. Glacial lakes, dammed by ice or moraine, can burst catastrophically when the dam fails, releasing millions of gallons of water in deadly floods called glacial lake outburst floods, or GLOFs. The Digsho Glacial Lake in Nepal burst in 1985, releasing 6 to 10 million cubic meters of water that traveled 90 kilometers downstream, destroying bridges, a hydroelectric plant, and farmland. As glaciers retreat worldwide, they create new glacial lakes in positions that may be unstable. The mountains hold water that could be released suddenly, threats that didn't exist a century ago when glaciers extended farther and no lakes existed in these locations. Avalanche dogs can detect human scent through 15 feet of snow. These specialized rescue animals are trained to search avalanche debris, their noses so sensitive they can locate buried victims that electronic beacons might miss. A well-trained avalanche dog can search an area in 30 minutes that would take 20 humans with probes several hours to cover. The dogs work enthusiastically, seeing rescue as an exciting game, unaware they're locating people whose lives depend on being found within minutes. Mountains have inspired humans to recruit animal allies, recognizing that our senses alone are insufficient for the challenges these environments pose. The deadliest mountain is not Everest, but Annapurna in Nepal. Roughly 40% of climbers who attempt Annapurna die a fatality rate that makes it the most dangerous of the world's 8,000-meter peaks. The mountain's faces are steep and prone to avalanches, its weather unpredictable and severe. Yet climbers continue attempting it, drawn by the challenge, the beauty, the simple fact that it exists. Mountains test us, and some people need to be tested to push against limits and discover what lies beyond comfort and safety. This urge has driven exploration throughout human history, sometimes to triumph, sometimes to tragedy, always to transformation. Mountains are laboratories for studying evolution in action. Isolated populations on different peaks evolve independently, becoming distinct subspecies or even species over thousands of generations. The Galapagos finches are famous, but mountains worldwide show similar patterns. Each peak, a separate island where evolution proceeds along its own path. Scientists can study how similar environments on different mountains produce convergent evolution-related species, developing similar adaptations to solve the same problems. Mountains accelerate evolution through isolation, while also preserving ancient forms in refuges where climate has remained stable while surrounding lowlands changed. Ropes used in mountaineering can hold 4,000 to 5,000 pounds, roughly the weight of 2 cars, yet they're light and flexible enough to coil and carry. These ropes are engineering marvels, woven from synthetic fibers in patterns that provide strength and stretch. The stretch is critical. Rope that doesn't stretch transfers fall forces directly to the climber, potentially causing severe injury. Modern climbing ropes absorb energy by stretching, then slowly return to their original length. Mountains have driven innovation in materials science, each technical problem spurring solutions that often find applications far beyond climbing. The Incas built roads across the Andes that spanned over 25,000 miles, connecting an empire that stretched 2,500 miles from north to south. These roads crossed mountain passes over 16,000 feet high, featuring stone steps, suspension bridges, and tunnels. Runners called chasqui carried messages along these roads, operating a relay system that could move information from one end of the empire to the other in days faster than any European communication system of the same era. Mountains were not barriers to the Incas, but a homeland to be embraced, infrastructure to be built, a landscape that shaped their civilization in profound ways. Machu Picchu sits at 7,970 feet, lower than many Andean cities, but spectacularly positioned on a ridge between two peaks. The Incas built this city without metal tools, draft animals, or wheels, quarrying and shaping granite blocks that fit together so precisely a knife blade cannot slip between them. The city clings to a mountainside, steep enough that a fall from the agricultural terraces could be fatal. Yet the Incas terraced the slopes for farming, built drainage systems that still function 500 years later, and created a urban center that has survived centuries of earthquakes. Mountains inspired architecture that worked with the landscape rather than against it, achieving durability through understanding rather than brute force. Mountain ecosystems shift upward as climate warms. Species adapted to high altitudes have nowhere to go when temperatures rise. They're already at the top. This creates escalator to extinction scenarios where species run out of mountain before they run out of climate tolerance. Pika's small rabbit relatives that live in talus slopes are retreating upward in mountains across the western United States, disappearing from lower elevations as temperatures exceed their tolerance. Eventually, they'll run out of mountain, and then they'll run out of options. Mountains that once offered refuge from climate change now become traps. The Tibetan Plateau averages over 15,000 feet in elevation, an area the size of Western Europe elevated high above sea level. This immense plateau affects global climate by forcing air masses upward, creating the jet stream patterns that steer weather across the northern hemisphere. The plateau's elevation means it receives intense solar radiation, heating the overlying air and creating pressure systems that drive the Asian monsoon. Without the Tibetan Plateau, weather patterns across half the world would be fundamentally different. Mountains don't just occupy space, they shape atmospheric circulation at continental and global scales. Yaks are domesticated cattle adapted to high altitude, with larger lungs, more blood hemoglobin, and metabolisms tuned for thin air. They can survive and work at elevations where normal cattle would die, carrying loads across passes over 18,000 feet high. Their milk contains higher fat content than lowland cattle, and their dung, when dried, provides fuel for cooking and heating in regions where trees don't grow. Yaks are perfectly adapted to mountain life, and the peoples who depend on them have built cultures around this remarkable animal, proving that domestication works both ways. Humans and yaks adapted to each other and to the mountains they share. Some mountains are hollow. Volcanic mountains often contain extensive cave systems, created by lava tubes. Tunnels formed when the surface of a lava flow solidifies, while molten lava continues flowing beneath. When the eruption ends and the lava drains, it leaves a hollow tube that can extend for miles. Kazumura Cave in Hawaii runs 40 miles through the slopes of Kilauea volcano, one of the longest lava tubes in the world. Walking through these caves is like traveling through the mountain's arteries, passages that once carried molten rock, now empty and dark. Evidence that mountains are not solid masses, but complex structures shaped by dynamic processes. Mountain glaciers flow faster in summer than winter. Meltwater at the glacier's base lubricates its movement over bedrock, allowing it to slide more rapidly when surface melting increases. Some glaciers surge episodes of rapid movement that can last months or years, advancing dramatically before settling back into slower flow. The Hubbard Glacier in Alaska has surged multiple times, advancing so rapidly it blocked the entrance to Russell Fjord in 1986, temporarily creating a freshwater lake. Glaciers are not static, they breathe and pulse, responding to seasons and longer cycles in ways we're still working to understand fully. The Bearschrund is a deep crack that forms where a glacier pulls away from the head wall of the cirque containing it. This crevasse can be hundreds of feet deep, a moat of ice surrounding the upper reaches of the glacier. Climbers must cross bergstrands to reach many alpine routes, leaping over dark gaps or finding snow bridges strong enough to support their weight. These crevasses reveal the glacier's internal structure, layers of snow compressed into ice over decades or centuries, sometimes showing volcanic ash from historical eruptions or other markers of time. Mountains reveal their history in layers when we look into the wounds that fracture reveals. Thunderstorms on mountains can be particularly violent because the peak itself can trigger storm formation. Air forced upward over the mountain cools and condenses, forming clouds that may develop into thunderstorms within hours or even minutes. Being caught above treeline during a mountain thunderstorm is terrifying. You're the tallest object for miles. Lightning striking peaks around you, sometimes striking the ground close enough to feel static electricity raising your hair. Metal Gear hums with electrical charge. The air smells of ozone. Mountains create weather that can turn deadly faster than you can escape, teaching humility to anyone who spends time in high places. Some mountain cultures practice sky burial, where the deceased are placed on mountaintops to be consumed by vultures and other carrion birds. This tradition exists in Tibet and other Himalayan regions, reflecting both practical concerns. Frozen ground makes burial difficult, and spiritual beliefs about returning the body to nature and feeding other beings. The practice demonstrates radically different relationships with death and landscape than those common in industrial societies. Mountains in these cultures are not recreational spaces, but sacred landscapes where life, death, and spiritual practice interweave. The Matterhorn has 4 faces, each looking different from different valleys. This gives the mountain its distinctive pyramid shape when viewed from Zermatt, Switzerland, but from the Italian side, it appears as a different mountain entirely. Perspective transforms mountains. The same peak can seem approachable from one angle and impossible from another. What we see depends on where we stand. A reminder that objectivity requires multiple viewpoints and that single perspectives always reveal only partial truths. Mountain building is happening right now beneath our feet. The collision between India and Asia continues at 1.6 inches per year, crumpling crust and raising the Himalayas higher. The Cascades volcanoes add material through eruptions. The Andes rise as the Nazca Plate subducts beneath South America. We live in an era of active mountain building, though the process seems frozen in time from human perspective. Geological present and human present operate on such different timescales that we struggle to comprehend processes unfolding over millions of years. Yet these processes continue regardless of whether we can perceive them. Mountains contain mineral wealth that has driven human exploration and exploitation for millennia. Gold, silver, copper, lead, zinc, many valuable minerals concentrate in mountain ranges where geological processes concentrate and expose them. Mining has scarred mountains worldwide, creating wealth for some while leaving environmental damage that persists for generations. The Colorado Rockies, the Andes, mountains across Africa and Asia bear marks of mineral extraction, evidence that humans see mountains not just as obstacles or sacred sites, but as resources to be exploited. The relationship between humans and mountains has always been complex, mixing reverence with extraction, preservation with transformation. The continental divide creates a strange legal boundary. In some places, water falling on one side flows to one ocean. Water falling on the other flows to a different ocean, And in some jurisdictions, water rights differ based on which watershed you're in. Property lines, state boundaries, and legal jurisdictions sometimes follow mountain ridges and divides because they're obvious, visible boundaries. Mountains shape human law and governance, providing natural borders that influence political geography from local to international scales. Glacial erratics are boulders carried by glaciers and deposited far from their source, rock, sometimes hundreds of miles away. These out-hoved place rocks puzzled geologists before the Ice Age theory was accepted. How did boulders weighing thousands of tons end up on mountaintops, far from any similar rock? The answer: glaciers transported them during ice ages. Seems obvious now, but was revolutionary when first proposed. Mountains hold clues to Earth's climate history in the form of these transported stones, evidence that glaciers once extended far beyond their current limits. The last major ice age ended only 12,000 years ago, a blink in geological time. During glacial maximum, ice sheets covered much of North America and Europe, and mountain glaciers extended far down valleys that are now ice-free. We live in an interglacial period, a warm interval between ice ages. Whether the current warming represents a permanent end to ice age cycles or merely a temporary warm spell remains uncertain. Mountains that once supported vast glaciers may support them again if climate shifts, or they may lose what ice remains if warming continues. The future is uncertain, but mountains will respond to whatever climate emerges, just as they've responded to climate changes throughout their existence. Mountains teach patience. They were here long before you, and they'll be here long after you're gone. They change, but on timescales that mock human ambition and urgency. Standing on a mountain, you feel the weight of geological time, the irrelevance of human concerns measured against the patient rise and fall of stone. This perspective can be humbling or liberating, or both, recognizing that your problems are temporary. Your life is brief, and yet you're part of a continuity that extends from deep past into distant future. You're made of atoms that were once mountain rock, that will become mountain rock again, cycling through forms in endless transformation. The summit is only halfway. Mountaineers often say the top is the halfway point because you still have to descend, and descent claims more lives than ascent. Exhaustion, reduced vigilance, gravity's assistance turning into a liability. More accidents happen during descent than climbing up. Mountains teach that success isn't reaching the goal, but returning safely. That knowing when to turn back is as important as pushing forward. That survival matters more than achievement. These lessons extend beyond mountaineering into life more. Generally, sustainable success means maintaining the ability to do it again, not burning yourself out in a single spectacular effort. As you rest tonight, mountains around the world stand in darkness, their peaks catching starlight, while valleys remain in shadow. Snow falls on some, settling silently onto glaciers. Wind scours others, plucking rock grains and carrying them downslope. A few volcanoes rumble deep within, magma churning in chambers that will eventually erupt or cool back to stillness. Climbers huddle in tents on some high slopes, waiting for dawn to attempt their summits. Wildlife moves through high forests and across talus slopes, hunting or grazing or simply surviving another night in harsh environments. The mountains don't sleep, they simply exist, indifferent to human observation or concern, continuing their slow transformation through time. Mountains have been teachers throughout human history. They've taught us humility by resisting our attempts to control them. They've taught us persistence by rewarding patient effort and punishing haste. They've taught us interconnection by demonstrating how elevation affects temperature, how temperature affects precipitation, how vegetation affects wildlife, how everything connects to everything else in systems too complex to fully predict, but simple enough to observe and partially understand. Mountains are classrooms without walls, teaching anyone willing to pay attention and endure discomfort in exchange for lessons available nowhere else. The attraction to mountains seems hardwired into many humans. We climb them because they're there, a reason that's simultaneously meaningless and profound. Mountains call to something in human nature, desire to test ourselves, to see what's on the other side, to stand in high places and look down on the world. This attraction has driven exploration, inspired art and poetry, motivated scientific inquiry, and shaped cultures around the world. Mountains have been gods and obstacles, resources and refuges, dangers and sanctuaries. They contain multitudes, meaning different things to different people, supporting diverse relationships while remaining fundamentally themselves, stone and ice, rising and eroding, eternal and temporary. The specific mountain matters less than what mountains in general represent: permanence in an impermanent world, beauty in harshness, challenge that reveals character, perspective that expands vision. You don't need to climb Everest to experience what mountains offer. A local hill serves as well as a Himalayan giant if you bring the right mindset. Mountains exist at every scale, from the Rockies to the gentle rises of ancient Appalachian stumps, and each has something to teach about geology, ecology, persistence, change. Tonight, as you drift toward sleep, imagine standing on a mountain at dawn. The sun rises from behind distant peaks, first lighting the highest summits, while valleys remain in darkness. Light travels downward like liquid gold, pouring over the landscape, illuminating slopes and forests, warming cold air, bringing color to gray stone. You watch this transformation, knowing it happens every morning, whether you're there to witness it or not. That mountains greet the sun daily, in patient repetition that predates consciousness and will continue after awareness has passed from this world. There's comfort in this continuity, in natural processes that continue independent of human witness. Mountains remind us that we're visitors in landscapes shaped over millions of years. We pass through briefly, affecting them hardly at all, despite our technologies and ambitions. They'll outlast our civilizations, eroding slowly toward the plains they'll eventually become, only to rise again elsewhere when plate tectonics builds new mountains from old sediments. This cycle has repeated throughout Earth's history and will continue until the planet's interior cools enough that plate tectonics stops billions of years in the future. An inconceivably distant time when mountains will finally stop rising and erosion will have won its patient war against uplift. But that future is so distant as to be meaningless to any practical concern. For now, and for countless generations to come, mountains will rise and fall, grow and erode, support life and challenge it, stand as monuments to geological forces and testaments to time's passage. They'll continue being mountains, complex, beautiful, dangerous, nurturing, indifferent, inspiring, offering whatever lessons we're prepared to learn from stone and ice and thin air. Close your eyes now and feel the stability of your bed. the solid ground beneath the building, the bedrock beneath the soil. All of it rests ultimately on the same tectonic plates that build mountains, floating on the slowly flowing mantle, drifting across Earth's surface at speeds too slow to perceive but fast enough to move continents in geological time. You're part of this system, made of recycled mountain stone, breathing air that has flowed over countless peaks, drinking water that fell as mountain snow. The boundary between you and mountains is less distinct than it appears. You're made of the same elements, shaped by the same forces, temporary assemblies of atoms that will disperse and reassemble in other forms when your particular pattern dissolves. Rest easy in this knowledge. You're home, not in any specific location, but in the larger sense of being part of Earth's cycles, connected to everything through chains of causation that extend back to the planet's formation and forward into a future beyond imagination. Mountains stand as visible reminders of these connections, monuments to deep time and slow transformation, anchors of stability in a changing world. May your dreams tonight carry you to high places where air is thin and clear, where stars shine brighter than you've ever seen them, where horizons expand beyond daily concerns. May you wake tomorrow with perspective renewed, remembering that your challenges, like mountains, are temporary features in a landscape that's constantly transforming. Some mountains you'll climb, others you'll walk around, and many you'll simply admire from a distance. And all these responses are valid because mountains ultimately exist for themselves, not for you. And their indifference to human concerns is part of their gift. Sleep well, dear friend. The mountains stand watch tonight as they've stood for millions of years, as they'll stand for millions more. They need nothing from you, expect nothing from you, offer their lessons freely to anyone willing to listen. In the morning, they'll still be there, patient as stone, distant as stars, familiar as breath. Until then, rest. Let the quiet knowledge of mountains anchor your dreams, their permanence a lullaby, their slow transformation a promise that change and stability can coexist, that what seems eternal today will eventually pass, and that what passes leaves traces in stone that tell stories to anyone who learns to read rock. Good night. May your rest be deep and peaceful as the silence between peaks, and may you wake renewed, ready to face whatever mountain's literal or metaphorical tomorrow brings.